Yes. Yes, so our speaker today is Peter Grove of Renesas, where he is a senior member of the technical staff, and he will be talking about a mixed signal universal test bench for RTL DMS AMS, which he calls UTB. Peter has worked in the industry since 2001 when he joined a small company called Wolfson MicroElectronics, where he was project lead for more than 15 production devices. Since then, Peter has only worked at one other company's, Nujira, before joining Dialog, which is now Renesas, at their Edinburgh office in 2014. Peter's background has been mainly digital design, but has over the years taken charge of many large mixed signal devices that are in volume production and has been exposed to enough analog design work to appreciate the issues they face in verification. Peter has an eye for looking at ways in which techniques can be done to improve chip level coverage, simulation runtime improvement, to name a few. And during his days at Wolfson, he was a key player in defining a schematic layout tool set with integrated revision control, which has allowed Peter to gather a large number of skills, not just in design work, but also in the back-end flows and EDA tools, understanding different net list types and how the tools work. Peter's technical interests are mixed signal and analog verification methodology and design flows. Peter is also an Acellera SystemVerilog-AMS committee chair, UVM-AMS member and key contributor, making sure the user's feedback on the language is considered and not what the vendors just want to support. He's, as I said, he's located in the UK, and we'll hand over to Peter now. Thank you, Peter.
Thank you very much for that, Mike. Okay, so today I'm going to give a broad overview of a universal test bench that we use at Renesas and how it all works together. So to start with, you know, often I get people creating a test bench that they can use in DV and DMS, and then they try and use it in AMS and it all goes wrong. And the main reason is the verification techniques that people use for DV and DMS don't align when you've got multiple discipline usage. So multiple discipline usage is something that you've got one discipline that is discrete in time, which is digital, and the other one is continuous time, that's, you know, analog. Also, you know, the aspects of where you generate stimulus and monitors from a digital point of view doesn't really matter, but when it comes to integrating that with an analog solver, there's some key important steps that need to be done. And all of this has implications on how you verify a chip in AMS. And the key thing is getting the verification engineers to switch their thinking to of how this can apply in mixed signal, not just in the DMS DV domain. Simple things like how many out of module references affect connect modules is an example. So really what the classical UVM test bench just needs to change slightly so that we can allow dual usage between DV, DMS and AMS. So today's focus is really on the mixed signal DMS AMS test bench and automation, but the actual automation I've got and I demonstrate works on a pure digital block as well today. There's a few acronyms at the top. DV I refer to as digital verification, or it could just be design verification. DMS is digital mixed signal, sometimes referred to as real number modeling, and the other one is AMS. So why would we want to bother with a unified test bench? Why not just leave it that the AMS people and the DMS people have their own environment? You know, why try and, you know, complicate matters? Well, often you want to share resources. Normally your digital verification is running ahead of any analog one because the analog ones take a lot longer to run. So if you can get engineers testing things using DMS up front, you want them to be able to quickly switch to AMS. So there's the training aspect. Then you've got verification IP that you might develop in DV and DMS that you also want to use in AMS. So the whole point of being able to share everything is important. The other thing, and this is something we do a lot on the Edinburgh site for Renesas, is we develop a lot of our test cases and validation using DMS models, and then we switch to schematics and we run the same test case. And the stage we've got to at the moment, our digital guys are able to literally flick a switch and run the same test in AMS without any assistance. So this gives us a real advantage. Instead of having to have multiple verification teams, we've really got one. Now, it's not to say that the DMS verification guy is an expert in AMS and isn't to debug the problems, but it means that he should out the box be able to get things going. It also avoids a lot of duplication of effort. You know, if you've got multiple test benches and styles for the different disciplines, then you know there's a lot of collateral for your engineering departments to constantly maintain. You know, and there's absolutely no need for that. And fundamentally, as a user point, if you're able to become a verification engineer who's mixed skilled, you're more likely to earn more. Because you've got a unique skill set that not many people have at the moment. So some key requirements to enable a unified test bench. We need to ensure that the driver, you know, that drives a pin of the DUT can change its abstraction very easily. So what I mean by that is if I've got the DUT that is, you know, a logic pin, but then I change the abstraction of that DUT by a model change, so it's no longer logic, it's a real or a UDN or electrical. I want to be able to change the driver to speak to it without having to regenerate a completely different test bench. And that's one of the key things that was I pushed into UVM-AMS. We also need to block out of module references. In DV and DMS, out-of-module references don't cause any problems. When you start having a unified test bench, the issue you have is you don't know when you're compiling that design whether that net is going to be digital or it's going to be analog, unless you go into every out-of-module reference and put a tick if-def in there and someone manually goes and controls, you know, how that net's going to be resolved. There are workarounds on this. So I presented a paper, it was in 2020, not 2022. I apologize, that's a mistake. And basically you use the VPI to do this. So to avoid problems, I set all our wires in the design as the word interconnect, which is part of the SystemVerilog language. And that blocks out of module references and sort of forces the DV guys not to do things that would break stuff in AMS. And that was one of the key things that we had to do to ensure a smooth transition from running a DMS sim to an AMS sim using the same test bench. One of the main reasons for this is it avoids a T-style connect module being inserted, which often causes lots of issues and they're really hard to track down. The other thing is, if you've got a very complex test bench that's now using UVM, SystemVerilog, and all the fancy verification techniques with classes, it's quite possible to cause the analog solver to fail to get a DC operating point. And therefore, it's really important that you make it easy to debug DC operating points, otherwise your teams are not going to use it. And that's from experience. So, and the other one is you want to limit the number of connect modules inserted in the test bench. You know, connect modules, you know, cost in simulation time. The more you put on, the more problems or the more connect modules you have on the same net, the more problems you're likely to have. So it needs to be structured in a way that it limits that number or optimizes it. So the concept we have is using the UVM dual top methodology. So we have two dollar root modules, a test case. So that's a module that just encapsulates all the stimulus, all the class-based stroke software layer. And the TestEnv, which is basically encapsulates all your physical stuff. So your pin drivers, monitors, external components. You know, it's basically what your PCB would look like. You know, and ideally, as we'll see later, having that TestEnv reside in a schematic capture tool has benefits. So a lot of people will look at this and go, why bother with the dual top methodology? Well, there's other advantages. The vendors have hardware accelerators, emulators, and what they need is they need a clear divide between the hardware layer and the software layer. So having a dual top like this, where we've split it into a test case that is all your software stimulus and a TestEnv that's all your physical modules, means that the physical TestEnv can go on one of these hardware accelerators. So we're reducing costs by, you know, maximizing the reuse between different dot abstractions. So I'm reusing my Testbench, whether the dot is using real number models, stroke DMS, and then again in AMS. And the automation part is useful because a common thing for a verification guy is to go and build a test bench, or even the designer of a block needs a test bench just to validate, you know, that it's functional. If everyone goes and does their own one, it's quite hard to share stuff. So automating that, you know, at least forces a common structure. So there are some requirements for the automation. We want to be able to generate the test bench from an RTL definition, a net list, or a schematic symbol, you know, because you could have your dot as a schematic. For pure RTL blocks, we also need to support complex ports, things like multi-dimensional arrays of packed and unpacked. The code I've tested it as a 6x6 packed and unpacked array. I'm pretty sure it will work for any combination. It also needs to work with SystemVerilog interfaces, parameterized ports. Now, all of that is only needed for RTL definitions, because anything that's coming out of a schematic capture port doesn't support multi-dimensional arrays. They're all one-dimensional, which makes it nice and easy. Key thing is also to make sure that the constructs and everything used is LRM compliant. You know, not only is this good practice, it means that you can use other tools to read the code, and vendor extensions normally are limited to just like the simulator rather than the entire tool chain. So it's better to work within the LRM. If not, you get your LRM updated, you know, rather than doing bespoke stuff. So the other one is with any sort of automation flow, it has to be easy. If the interface or the usability is hard, people will stop using it. They need something that's quick, easy to use, and robust. You know, if we pick up someone's script and it doesn't work, you normally won't use it again. So we also need to support the ability to have, you know, user code within some of the templates that we've got, and make sure it's preserved if regenerating the files again. We also need to make sure that the template code is good enough that users don't have to hack it. As soon as a user starts hacking anything that's in the template code, it means you've probably made a mistake or gone down a path that is incorrect. The other one is partitioning the file list and command line arguments. We'll go over that a bit later, but you want to be able to add and remove features from the runtime simulation without having to rework the entire file list. You know, especially if you're switching from DMS to AMS, you want to be able to just include, exclude a couple of .f files and make that switch rather than having a complete new one. And finally, if you're doing DMS and AMS, having it work in harmony with your schematic capture tool, Virtuoso in the case of what we use, is really important. So I'm often asked, why are we bothering to import the Testbench into the schematic capture tool? Why am I pulling in text views and things like that into a schematic tool? Let's leave it on the command line. Well, you can do that, but the schematic capture tools have a nice feature, such as a hierarchy editor and a net lister. So the hierarchy editor is a nice and easy way to configure the design via a GUI and actually see what different views you're using for different instances. You can do that in a Verilog configuration file, but it's not, visible in the sense that you can see exactly what you're getting. The net listers are very good at extracting the hierarchy and creating these Verilog binding files. Again, you can do them yourselves, but they're error prone. It also makes sharing the Testbench between DMS and AMS a lot easier. So the flow here is recommending that you import your Testbench into the schematic capture tool, and this can work whether it's a digital on top or analog on top flow. The pros of doing this is creating a binding file behind. It's error prone. Creating a lib.map and a Verilog configuration file, unless you know what you're doing, you're likely to make a mistake, and it might be really hard to find where that mistake is. Because if you've got two AND gates in the design and there's a subtle difference in like a timing of one of them, you might not notice, until late on, or might not notice at all that you've used the wrong one. It's far easier to stitch a design together in AMS, where SPICE uses the order connection, and having a graphical view allows you to easily root cause any problems. The cons, anything you put into a schematic capture tool basically has to be fixed. It can't have conditional topology. So you can't have a parameter in it that you would set, at runtime to say whether it's using this instance or this cell versus another one. So you can't change the topology. You generate statements can cause issues, as the net lister and the hierarchy editor would not know which path to follow. So there are a few limitations, but there's nothing in there that you can't work around. And probably the biggest one that I find to date is it's not what a digital guy would use. A verification guy is used to the command line stuff. So as soon as you go, you need to use a GUI for this. It's not something they're really keen on, but all of those can be overcome. So within the Testbench, we need some logic drivers and monitors. So these are for your digital ports, electrical drivers and monitors. So they're for your sort of analogy ones. And if you've got, a complex PMIC or audio, you're going to have some passive networks of components or analog load models that you're going to have on each of these pins. And you're going to have some UVC'S as well. Now, the key thing with all of this is if you're wanting to share the Testbench between DMS and AMS, your electrical driver is going to have a DMS version, and it's going to have an AMS version. Similarly with your passive networks. So it's not like you place what you want down and it's going to work in both. You need to have two views of each of these cells and make sure that they align. But that's some upfront work that once you've done, everyone can use. So a possible logic instrument for a driver monitor is depicted here. So the way I've done it is I've got a SystemVerilog interface that then connects to an API that I can then speak to from the test case itself via the software layer. And in there, I've got some very basic drivers like driving a clock, driving a pulse with strength control, driving ones and zeros. I've got some monitor in there so that we can get the value of this net, get the strength. I give it a VDD and VSS, and I make sure that if a connect module is needed for AMS, say that the dot pin here is electrical, it would insert the connect module on this boundary and not elsewhere. So all of that is great, but often your pins are not connected to something that you bit bash with ones and zeros. They're going to be connected to some UVC driver like an I2C. So what we've done is we created a port called bypass logic that goes via tran if statement to the LILO. So basically you can actually connect all your digital controls here to the same net and get it routed through here and get it driven out. The beauty of this is you end up with one connect module here rather than if you connected each of these UVCs to the pin, you'd have a connect module on each pin, and then in AMS you could be dealing with problems that this one isn't as tri-state as you were thinking. So the only maybe downside of this is a tran if does reduce the logic strength from supply down to strong, but I haven't hit an issue where people have said to me they need it strong. If they did, there are ways of dealing with that using the VPI. The extension of the logic instrument to make an electrical is fairly straightforward. We instance a logic instrument within an electrical one. The electrical one has the same sort of interface to connect to the class-based layer so that your test case from the software side can speak to it. Here, though, we have a core element, and that core element has to have two views. One's a SystemVerilog view, and one's a VERILOG-AMS view. The SystemVerilog view is there to provide a DMS stimulus, and the AMS one is there to create the AMS stimulus. And via a hierarchy editor, you could switch per instance or globally, whether it's using the SystemVerilog one or the VERILOG-AMS one. So the way this works is we've got some sine waves, ramp, generation. All of that is done in the core because it needs to be for AMS. And then the driver is placed here, and we've got a monitor there as well. So we've got a ref VDD and ref VSS so that your logic stuff is level shifted, and this is bidirectional, so that you could still have a UVC connected here and it would just drive out electrically on here. Or you could switch the pin and drive out a ramp as well. So very flexible. So one of the key things that I've had to push in UVM-AMS is that the analog signal generation must be done in the core. So it has to be done within this module here. The classical way of doing signal generation in UVM is you do it in a sequencer and your driver basically just drives out ones and zeros. When it comes to generating a sine wave and things like that, in AMS it needs to be done in the analog domain, otherwise you are likely to get incorrect results. So it ensures the right domain is used, which actually will ensure the best simulation runtime. People often think that if they generate it digitally it will be quicker. No, you can actually make it run a lot slower. So what we do for a sine wave is you'd pass in the frequency, phase, amplitude, send that to the electrical instrument core. That would basically then generate the signal. Any change in these values is seen as a D2A event that basically tells the analog solver, right, go and create a new analog solution at this point. So the whole point of this is you're wanting the analog solver to have the flexibility to choose the best time steps so that it's not forced to use smaller time steps than it needs by the digital. You know, if the analog can jump ahead using derivatives and clever algorithms to ensure that, you know, you get the optimum performance. If you generate your sine wave digitally, you create lots of D2A events that basically constrains that. So your DMS version of it then could be controlled on the number of samples you create per period for accuracy and performance. So yes, you can create the sine wave digitally, but there are some issues with that. First of all, you have to use the AMS transition filter that takes a discrete value and creates a PWL statement. It has to have a tolerance of 0. Your rise time and fall time must be exactly the same as the digital period, otherwise you've got an error. The problem is setting a tolerance of 0 on the transition filter is very bad for the simulator, and it wouldn't surprise me if most simulators ignored the value of 0 because you are constraining it so much it would probably fail to converge. D2A events may not exactly happen when the digital thinks it's happened. So if your digital event happens at 1 nanosecond, but the analogs created a solution at 1 nanosecond plus 1 femtosecond, it might think that that's close enough and therefore would use the 1 nano plus 1 femtosecond as the change point. You've just now put a nasty harmonic into your sine wave. And finally, the D2A events just can create unnecessary analog matrix solutions. So you could be actually causing the analog solver to go and solve the matrix every nanosecond when actually it's going, I can do it every 20 nanoseconds and still get a good enough accuracy, but you've told me I must do it every nanosecond. Similarly, the monitoring has to be done in the core. The reason for this is VERILOG-AMS has only one way of sampling an analog signal and putting it into a digital variable, and that's the ABS delta function. If you get it to be very coarse or accurate, it creates too many A to D events that will slow down your digital solver, such that the digital solver is slower than the analog. If you make the tolerances too big, you can miss key values. And unfortunately, there's no one size fits all on this. It has to be tailored for the specific signal that you're looking at. So it's sort of a non-starter to convert the analog signal into digital and do all the monitoring there. It has to be really done in the analog domain. So really, it's use the analog statement to implement the checkers and pass the result back to the digital. So other components can be built using this same methodology. What I'm showing here is sort of a slide that's part of UVM-AMS. So what the standard is looking at doing is having some sort of bridge that's a SystemVerilog wrapper that instantiates your proxy, an interface that speaks to an agent, and you've got an analog resource that you can then switch between different abstractions, where here I've got a VERILOG-AMS one and a SystemVerilog one. So the specification for the test bench is each pin has to have an instrument on it. The users have to have the ability to be able to add components to those pins, maybe an RC network. It needs to be able to support parameters to set the initial values. If I've placed a cap down, I want to set an initial value on that the UVM config DB knows about. We want it easy for people to hook up bespoke drivers like I2Cs, SPMIs, and want the users to be able to create arbitrary signals as well. And as I said before, using interconnect stops people doing out of module references where they shouldn't be. We also limit the code where user code should go. And we want to support multiple different test case or use cases. One is a chip level simulation for AMS and DMS. You've got a subsystem for DMS only, analog block, and then a pure digital block. So the structure we've gone for For the physical one, TestEnv is this. We have parameters that allow us to set the width of these bypass signals. They're currently not used. Basically, I came up with this idea, put it all together, and found that not all EDA vendors can handle the complexities and multi-dimensional arrays that this creates. So at the moment, it's fixed to 1. All the electrical instruments, we put in what we call TB analog ports, or the digital one in TB digital ports. That's really so your waveform viewer has a nice partition and it's not got a flat, 1,000 number of cells there. You have your DUT in the center, user components, analog components like caps, resistors, or loads, some analog stimulus if you want, and then the TB digital bypass, that's where you'd put your UVC'S. So as before, the DUT can be parameterized, SystemVerilog interface, and it's easy to add more. The DUT pins go to, all these 3 locations because you might need access to it. And everything is done structurally using SystemVerilog constructs only. So the physical structure that we've come up with allows us to basically have SystemVerilog interfaces on the ports there. Each of the individual bits of those ports goes to a logic instrument. I unravel the interface, so we have a logic instrument per bit. That gets reconnected up and goes through a SystemVerilog interface port here to your TB digital bypass logic, where you've got access to the interface again. The ref VDDs on this are used for AMS only, and similarly the bypass logic comes from here. And it basically means that you could have a UVC running through an electrical instrument or a logic without any issues. So how would I attach a UVC? So in the logic instrument, I set the bypass logic. Cost-wise, there's not much. It does net collapsing, so I just hook your I2C up to the individual bypass pins and it all works. I can do exactly the same if it's an electrical instrument. Say that those pins are modeled as DMS. I can do exactly the same here, and that all works fine. And I'm basically instantiating the I2C in a pure digital domain, and I haven't got to worry about the abstraction of the DUT. The digital bypass logics are initially all driven with 1-tick BZs on this port, and that's literally just so that you don't get warnings from your simulator about undriven in-out ports. You could attach, on the analog side, you might want a buck filter. So here I've instantiated an inductor and cap. Now, utilizing the simulator scheduling, I can basically reprogram those values on the fly pre-DC operating point. So the sort of usage we have is normal usage. The feedback is a load. LX instrument is left as tri-state because we don't want to do anything with it, and we can control the cap and inductor values via the API. So basically at time 0, we can reset these values to what we want. For ATE, we want these to be open. So we basically pre-time 0 via the API, we can open them up. And DMS, we can have different abstractions of these models as well. So what that means is that although we've got these physical components down here, and they've got default values, we can actually change them before the initial DC operating point happens. And that is very flexible. It now means your test case controls the test bench components rather than having to have a different test bench for each physical connection. So the test case is kept as a top level for the software layer. It imports the UVM, include file for all the user packages, the base package, you know, all your environment stuff, the base tests, you know, it's basically all the software layer, but it's sequenced such that the users don't have to edit the order. They've got control of it via an include package. We have one initial block for running the UVM test. And then from that, we've got a template test class that sets up all the instruments and components at time 0, DC operating point. The test case can then update that. So a resistor could be suddenly made an open, or it could be made a short, or it could be a special resistor value. So it literally allows you to reconfigure what is hooked up at time 0, where after time 0 doing that is not as easy. We set all the electrical instruments to be 0 volts or 0 amps, so a DC operating point is found easily. And so on the designs I'm dealing with now, where you've got, you know, maybe 500,000 transistors, my DC operating points are taking about 30 seconds, you know, because I'm not causing issues by having anything non-zero. Then all we do is we make sure that we consume some time before changing the values. So that's using the one step. So the reason for this is a lot of people aren't aware of how the VERILOG-AMS scheduler works, and that's key for this working. So at variable initialization, it either takes the default value of a real. So if you don't declare a value on a real, in AMS it defaults to 0, else it will take the value you've given it, similar with a class. It passes control over to the analog domain, where it executes all the analog initial begins. This is where it forms the matrix and sets the analog solver up. It passes control back to the digital, and this is where it will start to run through all the initial statements until it starts to consume time. So basically, this allows you, in this stage here, this allows you to go and reconfigure that resistor to be an open or a short or a different value. Once all the initial blocks have got to the stage that they're consuming time, it passes the control over to the analog, where it'll go and do a DC operating point, and that's an iterative process. So the phasing we've done is in the connect phase, we use the proxy to go and get all the parameter values from the instances. So like I've instanced a cap with a default value. This goes and reads it into the configuration database. Your test might modify it during the elaboration phase, and then just before the start of the sim, we go and apply those changes, and then we start the run phase. The first thing we have to do is we need to raise an objection. If this run phase is happening, we need to make sure it consumes time before the sequence starts. We put in this statement here that guarantees we consume some time before the sequence starts. And so this is the sequence to guarantee that between DMS and AMS we always get the same results, and we're not having values start at non-zero. So the make Testbench script, which is the crux of this, basically can take in multiple different inputs. It takes in a file list, a .v file, or internally we've got a configuration file. It can take a symbol view. From that, it generates an Excel file with the data. We call make Testbench with that. This basically creates our directory structures and all the files, and it goes and generates the test bench. So the key file after this, if you've got a mixed signal test bench, is this file. It is the Excel file, because this is what controls whether it gets an electrical instrument or a logic. So in a very simple example here, one sheet in the spreadsheet has a list of the pins of the module in question. the direction, some packed dimensions, unpacked dimensions. These are there as a reference for the user. Then they've got a way of defining the class and the subclass, whether it's an input or output. So the input class is either analog or, and the subclass basically defines how it should be treated at time 0. So if it's digital and you set that to digital input, it expects to drive a default value defined in there at time 0. If it's analog and an electrical, a V analog input, it expects to drive a voltage at time 0. And similarly with an output, it tells it up front what you should expect. But the instruments can be reprogrammed by your test case. So this is literally just setting up the initial one so that you don't have to do it in every test case. Then the VDD source here in VSS are what are connected to your ref VDD, ref VSS on the instruments to set the logic levels. So your normal workflow would be you run make testbench. If you need to edit the configuration file, you can. You save and close it, rerun the make testbench, and then basically from that, if it's a pure digital block, you can just kick off and run a sim. Everything's built for you. It won't do anything, but it will run a sim. If you're running the DMS and AMS flow, the recommendation is you import the test bench into your DF2 or your schematic capture, and then you would netlist extract from there before running a sim. And there's various tools that you can use for that. Additional things we've done to this spreadsheet is we allow the spreadsheet to auto insert some UVC'S so the users don't have to do it. Final thing I'm going to go through is file list partitioning. File lists or command line arguments have gradually got bigger and bigger over time. People aren't aware of what order things should happen. They seem to play around until they get something that works. So packages must be parsed before they're imported. So UVM is normally the first in the list because that's the first thing you import in any other package. Leaf modules should actually be parsed before they're instantiated, but actually most tools now can handle that. Make use of the -v and -y for libraries. We also want the file list to be ease of control. We want to be able to turn on and off code coverage, switch between GLS or RTL, switch between DMS and AMS without having to re-edit a file list. So you want to partition it cleverly or in a nice, clean way. So, this is not a definitive order, it's just a suggestion. You have a file with all the defines in first, you pull in UVM, you pull in your packages and other dependencies, you pull in your interfaces, and then you start pulling in all your module layer. So the sort of thing that our script does, it generates file lists for Cadence and Synopsys tools, and I partition it into like C code, common command line options, code coverage, UVC'S, messaging for turning off simulated controls, SDF, UVM, etc. So just trying to partition it in a sensible way that makes it easy to find where problems are. So like anything, there are limitations. I've built my Perl script using open source parsers. So, it's free, so it's not, the parsers aren't perfect. There are some more recent ones that look good that I might adapt from the Perl one. Getting some of the details of the IOs can be complex. Some require the information pre-elaboration and some require post-elaboration. So you sort of need a parser that's also got an elaborator in it. So if you've got some port that's parameterized and that parameterized comes from a package, there's search orders on which package it should come from if you've got multiple definitions. So that can't be done easily without an elaborator. So we use the Verilog Perl ones. So the things my script won't handle is nested system Verilog interfaces and ports that use packages to define the data type. But we don't hit that often. So, but it is something that, you know, if I got a good software engineer out there, I'm sure they could solve. So that was it for the presentation. There was a lot of material there, I appreciate, but it was all I could push in the time we had available. So I'd pass it back to you, Mike, or is it you, Sarah?
No, it's back to me, so thank you very much. And we have a few questions online as well, Peter. Hopefully we can stay.
Yep.
One's just a quick question. What's the advantage? Is there any benefit of using Excel over CSV files?
The main reason was Excel, we've got multiple sheets and we create lookup tables. So we've got all the error checking built into Excel.
Okay, all right, you actually build some error checking into that.
Yeah, so basically like, oops. So here, when you click on that, it's a pull down list. That's a pull down list. These are pull down lists. So it stops people putting a mistake, a typo in there that then is hard to find.
Yeah, I can see the advantage of that. Yeah, yes, okay.
It does work in OpenOffice as well.
Okay, that's interesting. So OpenOffice as well. Yeah, that's useful to know. Thank you. Another question. Typically, what percentage of tests from your regression suite of DMS runs do you redo with AMS?
I would say ours are very mixed signal chips, so a majority of our tests are to check the interaction between the digital and the analog. So a lot of them are rerun. If I had to do a ballpark figure, I would say at least 50%, if not more.
Yeah, I guess it's just maybe pushing towards the performance issue, isn't it? So
yeah, I mean, what we'll do is say we've got something in an auxiliary ADC that's got, you know, 100 inputs in it. We're going to build the test case using DMS, and then that one will be run in AMS.
Okay.
We use constrained random as well because you've got the power of UVM to do that.
Okay. Yes. Yeah. I understand. Okay. And are you able to set different levels of accuracy to adjust performance?
So depending on what if you've built your DMS test case and then you're running that in AMS, you would probably only convert the block of interest down to schematic and you'd leave the rest as a model.
Yes, okay.
Or you'd only the ones that you think are going to have an effect. But if you've got access to fast spice tools where they've got multi-rate simulators in it, then having it all as schematic doesn't really hit the performance too much.
Okay, so it depends a lot on the availability of tools, yeah?
Yeah.
Okay, thank you. Let me go to the next question. AMS test benches have a lot of models like long, short, W real, which will take a long time to run. Yeah. Do whether your UTB will be helpful there?
Yeah, you could switch. You basically switch your abstraction as to what is best. So we use user-defined net types internally, and you know and then we switch to analog where needed. But the whole point of like UVM-AMS is you could extend that your driver could use W real, you know, or whatever you think is best. I mean, it depends on the accuracy that you want versus speed.
Yeah. Yes. Yeah. Okay. And it's just a judgment on that balance, I guess, isn't it?
Yeah. I mean, again, if you've got access to a fast spice tool, one could say just run everything at transistors and take the hit.
Yes. Another question: how much randomization do you use in DMS versus AMS?
So the randomization is actually done by a colleague of mine. full randomization. We create the DMS tests that are randomized and then literally run the same ones in AMS. There are some specific directed tests in AMS that you'll want, like analog test bus checking, but if you've got, say, 10 LDOs that could start up in a sequence, you want to randomize the order of that sequence and just check that there's nothing wrong. So you do that in DMS and just do the same in AMS.
Got it. Okay, that makes sense. Okay. And just one last question is, I mean, people want to adopt this approach. What's their starting point, would you say?
I would. The starting point is really getting to understand how the instruments that I've got here. I mean, clearly I haven't shown everything about what we've done, but it gives you an insight as to, gosh, when I get to it, it gives you an insight of how to do the partitioning, you know, and if you use UVM-AMS, you know, start to go down this route. This is the complex thing to build.
Right, okay.
And once you've built an electrical one of these and a logic one of these, or one for a resistor cap, etc., then you've got everything you need for the test bench.
Okay, so that's the starting point, is it? The
yeah.
UVM-AMS build. Okay. Okay. Yeah. Okay, that's very helpful. Thank you very much, Peter.